The internal configuration of the Orion crew module is optimized for a crew of 4. During flight, the primary piloting responsibilities fall to the commander and the pilot, seated in the forward left and forward center positions of the capsule. The layout of this console is strictly dictated by anthropometric data. To guarantee accessibility during moments of high physical stress, the primary display units and interface elements are positioned exactly 1 arm's length away. This cockpit architecture abandons the manual stick and rudder controls of the Apollo era. Artemis utilizes a managed complexity model, replacing analog switches with highly automated digital systems. The central engineering problem of deep spaceflight is the pilot. The human body is a biological component that fails under extreme physical loads. High-frequency acoustic vibration and intense gravitational forces rapidly degrade both sensory processing and motor function. This biological fragility stands in stark contrast to the sheer mechanical power propelling the crew. The Space Launch System generates 8.8 million pounds of thrust to push the vehicle into orbit. To prevent physiological degradation from compromising the mission, the interface must act as an active filter. It relies on mechanical resistance and software logic to translate a failing human input into a safe, precise vehicle command. Because these interface filters are built on rigid, deterministic physics, the boundaries they enforce are entirely mathematical. By mapping the exact equations behind those logic gates, we can recreate the same flight constraints in a digital environment, turning a physical cockpit into a portable piece of software. Operating a spacecraft in a vacuum requires a different physical vocabulary than atmospheric flight. There is zero aerodynamic damping. An input that would gently bank an airplane will send a spacecraft into an uncontrollable, fatal spin. The primary tool for managing 3-axis rotational movement, pitch, roll, and yaw, is the rotational hand controller, gripped in the pilot's right hand. To prevent launch vibrations from triggering thruster firings, the rotational hand controller features a strict 0.25-degree deadband. Past this null zone, a parabolic shaper takes over. Small deflections yield precise bursts, while pushing the stick to its limit caps rotation at exactly 20 degrees per second. On the left side of the display sits the translational hand controller, granting the pilot authority over linear motion along the X, Y, and Z axes. This is a vector representation of the translational hand controller mechanism. To deflect the stick a mere 0.5 inches from its center null position, the pilot must apply exactly 2 pounds of physical force. During high-stress proximity operations, heavy tactile resistance prevents the pilot's hand from slipping into a target. If a pilot commands simultaneous forward and downward translation, the software intervenes. Hard-coded X-axis priority logic severs the Z-axis command, guaranteeing forward closing velocity is maintained. Artemis hand controllers do not act as passive joysticks. They are mechanical algorithms that enforce strict mathematical boundaries on human intent. That intent is visually confirmed through the Orion glass cockpit, a software-defined architecture that renders over 60 different display formats across 3 primary LCD screens. During the SLS ascent, sustained gravitational forces compress the pilot's internal organs against their seat, and heavy structural vibration actively blurs their visual acuity. Reaching forward to tap a specific button on a touchscreen during the period of maximum dynamic pressure is physically impossible. NASA solved this by mounting the cursor control device directly onto the seat armrest. This allows the pilot to operate the entire interface while their arm is fully supported. The caged castle switch features physical barriers restricting movement to horizontal and vertical inputs. Eliminating diagonal drift prevents the cursor from floating. The pilot makes deterministic, grid-based selections, snapping cleanly between menus, even while their arm shakes violently against the seat. If a fault is detected during this turbulence, the software generates an electronic procedure. Instead of just sounding an alarm, the system cues the required checklist on the display, highlighting the exact on-screen toggle the pilot must press. Under intense physical stress, the interface stops passively presenting data. It actively guides the pilot's cognitive process and physically restricts their motor inputs to ensure mission survival. The rendezvous, proximity operations, and docking phase of Artemis 3 requires the first human-crewed spacecraft docking in deep space. Orion navigates this sequence using high-resolution 3D maps generated by light detection and ranging sensors, routing that telemetry straight into the glass cockpit displays. On the primary flight display during approach, the pilot continuously tracks range tapes for distance, monitors H-dot closure rates to manage approach velocity, and keeps the error needles perfectly aligned on the ADI ball. The target they are approaching is SpaceX's Starship human landing system. Boarding this spacecraft introduces a stark contrast in engineering philosophy. The Starship flight deck replaces physical switches and tactile redundancy with massive touchscreen panels, leaning heavily into automated software integration. Because the Starship flight deck sits nearly 50 meters above the landing pads, the pilot cannot look out a physical window to guide the vehicle down to the lunar regolith. This diagram demonstrates the autonomous landing and hazard avoidance technology. It solves the visibility gap by stitching together a synthetic view from external cameras, overlaying digital hazard grids onto craters and steep slopes. During final descent, the pilot monitors the synthetic feed to verify the landing zone, ensuring Raptor engine plumes don't excavate deep craters. If unsafe, a single tap on the touchscreen recalculates the descent vector, translating the ship laterally to a safer patch. A successful Artemis 3 mission requires a pilot to navigate two fundamentally different approaches to flight. One relies on the tactile feedback of redundant physical hardware, and another trusts entirely in software-driven synthetic vision. Returning to Earth introduces the highest kinetic energy loads of the entire mission. The Orion capsule strikes the Earth's atmosphere at a velocity of 11,000 meters per second. To manage the massive heat buildup, the spacecraft executes a skip entry maneuver. By directing the lift vector, the capsule physically skips off the dense atmospheric boundary layer, extending its target landing range by up to 4,000 miles. An onboard algorithm called PredGuide continually runs numerical predictor-corrector models to calculate the exact bank angle required to survive the thermal load and hit the recovery zone. If the primary guidance computer fails, the pilot must manually fly the spacecraft through the plasma field using the backup Precision Loads Manage system. During manual reentry, the bank error needle is critical. If it drifts outside the safe corridor, the trajectory is fatal. To zero the needle, the pilot executes a bank reversal, aggressively rolling the capsule 180 degrees to flip the lift vector and reverse lateral drift. The guidance software runs shortest time logic in the background. It calculates rotational inertia in real time, instantly displaying whether a left or right roll is the fastest mathematical path back to safety. Surviving re-entry is not about traditional flying. It is the execution of algorithmically verified micro-adjustments inside a rapidly narrowing window of physics. The entire Artemis pilot experience is defined by translating human biological intent through rigid mechanical constraints and strict mathematical algorithms. The 0.25-degree deadbands, the parabolic force curves, the shortest time logic, all of these parameters are exhaustively documented by NASA. They are entirely deterministic. Because they follow exact rules, these physical hardware constraints can be perfectly translated into digital physics engine parameters. This documentation allows us to build a high-fidelity simulation using standard web APIs. We can generate the exact frequency of the master alarms using the Web Audio API and render real-time telemetry on an ADI ball using the Canvas API. Dedicated hardware simulators and VR headsets cost hundreds of dollars, require specialized equipment, and present high barriers for accessibility. A web architecture requires zero installation. This is the Artemis pilot project. It allows any user to access the precise operational logic of the Orion and Starship flight decks instantly from any standard browser URL. When a user feels the intentional lag of the parabolic shaper or struggles to center a needle during a bank reversal, the engineering trade-offs of deep space flight become visible. Even without a haptic cockpit, the visual feedback of these mathematical limits illustrates why the vehicle behaves as it does. By abstracting $100 million of aerospace engineering into open web technologies, NASA can bypass physical barriers and place the entire Artemis generation directly into the commander's seat.